Hi, and welcome to the next lecture of the BME course, which is about features or signatures that you can find in the brain signals. You can find a whole section on it in the paper from Van Gerven from 2009, and here I will give you verbally my explanation of it. So the sub-goals we have for this processing step is that you need to be able to list and at least 3 EEG features or signatures that can be used as input for a brain-computer interface. You need to be able to describe what kind of stimulation or task you would need to present to the user to elicit such EEG features, and you need to be able to evaluate the pros and the cons for using particular features. This is very difficult, so I don't think I will test you on this a lot. Okay, but try. Okay, so before we start, I have to explain to you how we can divide different types of brain-computer interfacing. And there have been several distinctions made. You can say, okay, we divide them based on the location of the sensors. So some people speak about non-invasive brain-computer interfaces versus invasive brain-computer interfaces. Another way to separate them is to sort them according to the feature in the brain activity that we use. That's this categorization. And Walpole and all have made a very nice paper out of this. So for example, features you can use are slow cortical potentials, sensory motor rhythms, event-related potentials, or steady-state visual evoked potentials in the EEG. I will show you some examples in this lecture. They are related to 3 different paradigms of brain-computer interface input that are distinguished by Zander et al. In this nice paper. And he distinguishes between 3 different types. The first is an active BCI, a reactive BCI, or a passive BCI. And I will give per brain-computer interface, I will give one example that is related to it, and then I hope it becomes clear to you. But this distinction is based on the amount of conscious control by the user. What do we mean by that? Okay, let's look at the most traditional form of a brain-computer interface, which is an active brain-computer interface. It is the idea that a user produces voluntarily control of the physiological signals. So I think of something, and my brain signals are being sent to a brain-computer interface, and the brain-computer interface gives feedback to me as a user, and I learn how to control a device with my brain signals. So I have to put my mind into 2 different states. And for example, traditionally they have gave you some kind of a ping pong game on a screen where you have 2 targets, a bottom target or a top target, and then a ball would start to move from left to right in the screen, and you are trying to push the ball to try to hit the target. Sorry, this was the target. To be able to do that, I have to put my brain signals into a certain mind state that the brain-computer interface can classify. So I need to have direct feedback of my signals, and I need to be rewarded for correct behavior. Psychologists would call this operant conditioning. So for example, we could use slow cortical potentials as a feature of the brain signals to do this. Slow cortical potentials are, as the name suggests, very slow potentials in the electroencephalogram that have a range of 100 milliseconds to several seconds that you can measure them. And they come from the cortex, so the upper part of the brain. And here you see the amplitudes changing over time. So this is from 0 seconds to 2 seconds. And you see a fluctuation in negativity arising over a couple of seconds. And the good thing is you can do this yourself. You can make your slow cortical potentials more negative in your cortex by thinking certain things. What do you need to think about? Imagine that you stand in front of a traffic light with your nice sports car. And you know that the light is about to jump to green and you can hit the gas and go away. In the moments just before the light becomes green, you anticipate that you have to give a reaction. At this moment, your cortex, your brain, prepares for this movement, prepares for this action, and you will see a negative slow cortical potential to prepare your brain to act fast in the next moment. And this is the kind of feature that we use for brain-computer interfaces. We can train people to produce slow cortical potentials. So for example, here in a first session with a participant, you prepare the people that at a certain moment a tone will appear, and from then you have to try to move a ball in the top rectangle or a bottom rectangle with your slow cortical potentials. After a while, when people have practiced this, you see that they're able to differentiate. The yellow line is when they try to hit the bottom rectangle, and the red line is when they try to hit the top rectangle with their slow cortical potentials. Now this difference in amplitude between slow cortical potentials is something that a brain-computer interface can detect and use for actually very literally the vertical positioning of a cursor. So we can use it to control a cursor on a computer. Sensory motor rhythms are another example of an active brain-computer interface. They derive from the following. If you look at, again, a normal EEG recording from somebody, for example, look at this electrode, electrode 6, which is placed over sensomotor cortex, and you see here the recording. You see that there is a large rhythm present in the EEG right up until this moment. At this moment, the participant is clenching his fist. He's clenching his fist. He's doing something motoric. And what do you see happening to the EEG pattern? You see the amplitude of the frequency disappearing. So the signal becomes much smaller until the participant relaxes again, and then you see the amplitude becoming bigger again. Now we know that there is a rhythm within the brain. We call this the sensory motor rhythm, or the mu and beta rhythms. Don't bother so much about this. But we can measure them over the motor cortexes. They're in the same rhythm as the alpha rhythm, 8 to 12 hertz. And normally when you relax, when you don't do anything, this rhythm has large amplitudes. But when you make a movement, the amplitude becomes smaller. Interestingly, the amplitude also becomes smaller when you think about making a movement or when you observe somebody else making a movement. So this makes it an interesting feature to use in a brain-computer interface, because we can instruct a participant that if you want to move a cursor up, you think of nothing. If you want to make a cursor go down, think of moving your hands, for example. And then you see that the mu rhythm, this would be the mu rhythm in the relaxed state. But when I think about moving my hands, I see the amplitude decreasing. And this change, this difference between mental states, is something we can measure and use for output to a brain-computer interface. Okay, So that's an active brain-computer interface where you voluntarily produce a brain signal by having some kind of mental imagery. A reactive brain-computer interface is one in which the user is looking at stimuli or hearing stimuli, and we try to evoke a response from the brain. So we try to figure out which stimulus do you attend to, and we can interpret that and give it back to the user. Let me give you an example. This is very difficult, I understand. So one feature that we use for a reactive brain-computer interface is the P300 event-related potential. Now, this is a feature that is elicited, induced in a user if we present somebody a sequence of standard stimuli. For example, monkeys. I'm going to show you monkeys, okay? And I give you as a research participant a task to count the oddballs. For example, the elephant. And the elephant should be presented less frequently, so they trigger your attention. You think, aha, there is the elephant. So the P300 is kind of the aha feature. Pay attention. Did you see it happening? So your brain gets used to the monkeys. It doesn't give a lot of response anymore to it every time you see a monkey. But then, aha, an elephant, and you see a P300 arising. And as I explained in one of the former lectures, the P300 stands for a positive peak after about 300 milliseconds. P300. We're not so inventive with names in psychophysiology. We can use this P300 in a brain-computer interface. How? We've invented a clever way for this. So we can place all of the, for example, if you want to let a person spell a word with their brain activity, you have the participant look at a matrix with all the letters included, and you have to focus on a certain letter. For example, now he has to copy the words hands free, and now he wants to spell the letter R. We now start flashing the rows and the columns of the matrix, and the participant has to pay attention to all the times that the row and the column where the letter R is being presented in is flashed. Let me show you this. So the rows and the columns start flashing. The participant is paying attention to the R. And this makes the row and the column that is flashing is now the elephant. All the other rows and columns are the monkey. You try to ignore the other rows and columns. But that row and that column containing the letter R is the elephant. And the brain-computer interface can decipher which one you're paying attention to and then predict which letter it is that you want to spell. And now you see the participant spelled the letter R. I hope this is clear. So this is a reactive brain-computer interface. Finally, a passive brain-computer interface. And this is nowadays much looked into, especially when we want to make more natural user interfaces for people. What if we can extract information of the user state from physiological signals? For example, information about your emotional state, your cognitive state, or your physical state, and use that to adapt human-computer interaction. The Nekomimi that I showed in a past lecture is a nice example of such an attempt. What if the device would know which emotional state you are in? So for a passive brain-computer interface, you don't put in any voluntarily control. The thing is just on top of your head or in your brain, maybe even. It measures your state and it helps you to adapt to certain devices. Okay, so now we've looked at 3 different EEG features, the 4 actually: slow cortical potentials, the sensory motor rhythms being divided in the mu rhythm and in the beta rhythm, the P300 event-related potential, and you could use emotional information. We've also looked at ways of stimulating, or the tasks that you need for a participant to do this. For example, to prepare yourself for a traffic light. This means that you're trying to make a slow cortical potential. Or for mu rhythm, if you try to change your mu rhythms in the EEG signal, you try to imagine certain types of movement. And when I want to evoke a P300 event-related potential, I have to present stimuli, frequent stimuli, to a user until one of the stimuli is different, and that evokes a P300 event-related potential. Now, the pros and the cons for using particular features. This is something I've studied in my PhD thesis. Well, think about it. The slow cortical potentials, you need around 4 sessions to be able to learn how to control this with your brain. So it needs training time. Whereas the P300, we've discovered, works for almost everybody immediately. You put all of the training on the computer instead of the human. So the human doesn't need to learn this, we can decipher it. However, as you can imagine, if you see those rows and columns flashing, and you need to be presented with stimuli all the time, it's a bit psychedelic. So it's annoying in terms of user experience. And so for every feature that we use in the brain signals, we have to decide, do you want a very effective signal? Do you want a very user-friendly signal? And these are difficult things to decide. And for this, we need a lot of I think more psychologists and more people like you who do interaction technology, where you understand what people really want. Okay, that was it for this lecture. I put the slides online, and thank you for your attention.